Bonjour à toutes et à tous. Je m'appelle Yves Delin, je suis professeur à l'université de Grenoble et j'ai l'honneur et la chance de présider cette instance de thèse de doctorat aujourd'hui de Madame Amal Gueroudji. Avant de vous passer la parole pour les 45 minutes de présentation, je souhaiterais présenter les différents membres du jury, en commençant par les deux rapporteurs et en commençant par le plus éloigné géographiquement aujourd'hui et durant la rédaction des rapports, c'est-à-dire Gabriel Antoniou, qui est directeur de recherche à l'INRIA de Rennes. Bonjour Gabriel. Et Laurent Colombet, donc notre rapporteur, qui est directeur de recherche au CEA d'AM. Les autres membres du jury seront Robert Ross, qui est senior scientist à Argonne, ainsi que Bruno Raffin, directeur de recherche à l'INRIA Grenoble-Alpes et directeur de thèse. Nous avons aussi deux invités dans le jury qui sont Madame Virginie Grand-Girard, qui est directeur de recherche au CEA, et Monsieur Julien Bigot, docteur en sciences, membre du CEA Saclay. Voilà, donc nous avons maintenant la chance d'écouter votre exposé pour 45 minutes, qui sont suivis donc des questions des membres du jury.
Thank you all for being here. So today I'm going to talk about the work I have been doing during the 3 years, which is entitled Distributed Task-Based Institute Analytics for High-Performance Simulation, which is co-advised by Bruno Raffin from INRIA and Julien Bigot from CEA. Thank you. So, as we all know, we are in the exascale era where we have the possibility to generate large data sets, and we are able to process 10 to the 18th power of floating points per second. And large-scale simulation generates huge amounts of data. For instance, for Gisela, it generates the order of 2 terabytes per time step, and it runs over thousands of iterations. Generally, the generated data by simulation is first written to disk, then read back for post-processing. However, this is not possible anymore because of the I/O bottleneck. The CPU performance has increased several orders of magnitude compared to the disk bandwidth. So we cannot first we cannot write all the generated data to disk, and we cannot also write all the generated data to disk. And the way or the simplest way to reduce the quantity of the data is to make selections in the time steps. However, this way we can lose a lot of interesting events and informations. So there is another way to reduce this quantity of data, which is called in-situ workflows, where we process the data while they are generated in the same supercomputing platform. And here we have several tools that are already interesting and that exist already, such as Damaris, that dedicate cores for in-situ processing. There is Sensei, SmartSim, and also visualization tools that support in-situ analytics and so on. However, those tools are so complicated to set up, and that's mainly due to the fact that most of them are built on the MPI programming model, which is inherited from the host simulation, which is, of course, suited for regular applications where we have computations, communications, and sometimes some synchronization. However, it's not the most suited for data processing algorithms that are characterized by the fact that are irregular. They are characterized by irregular data structures, communications, and control. And if we have a look, we try to have a look into the big data ecosystem, we find higher level programming models that are more suited for such irregular algorithms, such as task-based programming models and MapReduce. In this work, we have been working with task-based programming models. And here, actually, we have several frameworks and works that are already built on Python, so they are really easy to use, such as Parcel, PyComps, Dask, and Ray. They are also characterized by the fact they are dynamic, so they are more adapted for those irregular algorithms. To give an example of how this task-based programming works, we have an example here using Dask that we're going to use in that we have used in this work. So the idea is that we're going to create the tasks. We have the possibility to create a large array that is similar to NumPy arrays and read in parallel those data. Those tasks are for reading data. Then we can sum up those tasks and create the aggregate sum. And this is due only by the .sum function here. We can also use our own functions by only decorating the Python function and use it to do some analytics. For example, here a product of the S and the 2023, and then we are gonna get the result. So here we are just creating the task graph lazily, and it's only by calling the dot compute that we really compute the data, the results. And to show how it works in Dask, so this code is written in the client, which is the entry point to the Dask cluster. So this, to read the data, it has just to read some metadata from the parallel file system. It can use it to construct the task graph, as I have already shown. And then when it is constructed, it is submitted to a scheduler. This scheduler is a runtime that decides where to put those tasks. And once this is done, the scheduler will send those tasks to the different workers. And it's only at this step that those workers will read the data and process it in parallel. To give you another more complex example, and actually that's why we have opted for Dask. That's due to the fact that in Dask, we have already parallel versions of well-known libraries such as NumPy and scikit-learn. The parallel versions are Dask Array and Dask-Amal here. So we wanted to compute the incremental IPCA. It can be done by scikit-learn easily, sequentially. And the interesting thing is that we can use the exact same code to do it in parallel using the Dask Array and the Dask-Amal libraries in Dask. So from the user point of view, it's really satisfying to find the post-hoc version in parallel. So our goal is actually to get this simplicity to the world of In-Situ. So we bring together the post-hoc easiness and productivity and the In-Situ performance as it allows to bypass the disk accesses and the I/O bottleneck. In computer science world, we want to couple MPI simulations with distributed task-based In-Situ analytics using Dask. Now let's talk about the theoretical frame of this project. As we all know, an MPI program is actually represented by a set of processes that have their processing units and memory units. They do communicate between each other, and they may do synchronization. So if we have to present a code, we can consider two main dimensions: the space dimension, the processes, and the time dimensions. And here the data is updated at each time step until the end of the simulation. In a task-based model, as I shown you already, a program is represented as a directed acyclic graph where the nodes are the tasks and the edges are dependencies between those tasks. And the scheduling of those tasks in the resources are done by a runtime, which is in the case of Dask called the scheduler. So to recapitulate about Dask, we have three main actors. We have the client that is charged of creating the task graph, either by using higher level libraries such as Dask Array and Dask-Amal, or using more specified low level decorators such as delayed or the futures. Once the task graph is created, it is submitted using dot compute, for instance. When the task graph is received by the scheduler, it is used to populate the internal data structures of this centralized scheduler, and the scheduling algorithm which is used in Dask is called transition algorithm, simply because it just analyzes the states of the different tasks and decide at what time it will switch from a state to another state, depending on the dependencies that we have in the task graph. And finally, the workers are just simple processes that are in charge of really executing the different tasks. So when it comes to coupling those two different programming models, actually we are dealing with different concepts and that are recent here. So MPI, in MPI, we can define a data as a value of a given buffer at a given time step. So this data is mutable and it is local to each process. However, in distributed task-based programming, we talk about inputs and outputs of a given task, which is not the same way to see a data. They are usually immutable. The same data can be accessed by several tasks. In terms of communication in MPI, everything is explicit by the users, by the user in the code. So we know at which time we're going to have a given communication. They can be point-to-point or collectives. And in the task-based model, the communications actually are generated and optimized by the scheduler. We do not know which worker will communicate with which worker at a given moment. So that's done dynamically, and it is done by the scheduler. The communications in Dask, for instance, are done through remote procedure calls. Finally, the scheduling is explicit in MPI because we know which process will process which data at a given moment. However, it is implicit from the user point of view in Dask because this is done by the scheduler at runtime. So now let's talk about our approach and implementation. The main contributions of this work is the introduction of this bridging model that allows the communication between MPI and task-based programming model. We have implemented the library of this bridging model, which is called Dask-enabled in situ analytics, or DEISA. And we have actually two main versions: the multi-graph version, which is based on Dask key management system, and a single graph version, which is based on our newly introduced external tasks in Dask. To show how this bridging model work in a producer-consumer example, we can see that as two separated components. The first component is the MPI component, where we have tasks already assigned to the resources. They generate pieces of data that are the values, and those values are given to the delivery facility that will translate the identification of the data in MPI to another global identification that can be understandable in the other delivery facility of the task-based component, where here we describe the program as a given task graph. And those data then translated to other, the identifiers are translated to other identifiers that can be understandable and usable in the task graph. So as you have seen, we have, to do that, we have introduced four main concepts: the component, which is the parallel application and the associated resources; the data task is all the work which is done by a component which is delimited by two external tasks, internal and external events. Internal and external events are simply either intra or inter component communications, and the delivery facility will assure the communications between the two components. Concretely, in the implementation, our MPI component is the simulation. The task-based component includes all the Dask cluster that has the client, the scheduler, and the workers. The external events are implemented using PDI data interface. that I will present in the next slide. And the delivery facilities, we have implemented the libraries that ensure the bridging from the simulation point of view, which is called DEISA bridge, and the DEISA adapter from Dask point of view. So PDI is the data handling library that we have used to extract the simulation data for external use. It has its own data model where we describe already the data generated by the simulation as an array, and we give its size and so on. And actually, the good thing about PDI is that we can use it to instrument the simulations and use several plugins, either for IOs, for in situ, and so on. And in particular, it supports Python, so we can use it to call our library. So coming back to the delivery facilities, the bridge is built on a lightweight client. It is associated with each MPI process. From the Dask side, we have only one adapter for all the cluster. As I have said, they ensure the communications, either data and metadata, and all the communications are done through the centralized scheduler, either through the distributed queues that are accessible by both bridge data facilities or by using global variables. So internally, we have used in the implementation the PDI Pycall plugin, which we'll call the DEISA library. We have explored what is called pure data tasks that are simply pure data arrays that can be included in a task graph to make the simulation data as input to the task graph. We have reproduced the data coherence based on the Dask arrays, thanks to the Dask managing key management system. So this version is multi-graph version, and tasks can only be submitted after the data is sent to the memory of the workers, because we need Dask to generate the key that make reference to that data. In terms of architecture, here again we find the two components. So in the bottom we have the MPI simulation, which is represented by the processes communicating by the communicator. And in the top, we have the scheduler, the workers, and the client. So every time the data is available, it is extracted by PDI and sent to the bridge. The bridges will first send the data to the workers, get the reference that is sent to the scheduler as a metadata and other metadata. Once this is done, the adapter from the client side will get the metadata, and then the client can use this metadata to create task arrays and task graphs that it will submit to the scheduler. Then the scheduler can send all those different tasks normally as it does in postdoc. In terms of operation, we have three main steps: the initialization step to initialize the communication between the two components. Then this data available step, it is done every time data is available in the simulation. And finally, at finalization, we clear everything and disconnect all the bridges. So at the initialization step, each bridge will connect the client to the scheduler. It will get the list of connected workers to be able to send data to them, and it will send some data to, it will create its corresponding queue in the scheduler. The same way, the adapter will connect its client, create the variable where we put the list of the workers, and get access to the same queue where it will fetch the metadata. So in terms of the delivery facility in the simulation side is a set of all the bridges, the distributed bridges. So in this solution, we have to have n clients, where n is the number of processes, and distributed queues and a shared variable. In terms of data exchanges when data is available, so the bridge will first send the size, the position, and the time step as metadata to the scheduler. Then the adapter can get access to it. Then it will send the data to the worker that includes a communication to the worker and a communication to the scheduler. And finally, it will send the future return, the reference to the data in the scheduler, this future will be sent again in the same queue to the adapter. So there is actually two synchronization here between the two delivery facilities. Once this is done, we have to get all the data from all the queues. We can create a Dask array and get again the coherent version of the data, and we can at this time only submit a task graph. So it is done at each time step. In terms of communication, here we have 4 RPCs for each bridge, and in the other side we get 2 metadata. So we have 2 RPCs to the scheduler, and N represents again the number of processes. In terms of configuration in the Pycall plugin of PDI, the same thing. We can find again the initialization step where we send all those informations to the scheduler to initialize and connect the bridge. The second step is at each time when data is available. So we call the bridge.publish data that will send both data and metadata. And finally, at the finalization, we clear all those data. So here we have an example of this multi-graph analytics. I have taken the same example, which is an incremental PCA. Here is the way how we do it in postdoc. So we read the data, and then we can use this available already IPCA to use it. In the other side, instead of reading the data from the parallel file system, we get the data directly from the adapter, which is constructed here. And we have this for loop to get the data, then process the IPCA. So at each time step, we have to submit again a new task graph. So the takeaways from this version is that we have dynamic task submission. We can submit different graph at each time step where we can send whatever we want. However, we have to send a lot of metadata at each time step. We have to manage the time dependency manually, which is a bit complex when we don't have the incremental version of a given algorithm. And we have to send all the generated data per time step, even if we don't need it for computation. So we have implemented another version, which is the single graph implementation, where we have our own distributed key management system to avoid all the communications to the scheduler. We have improved the scatter operation that sends data to the worker from the bridges. Thanks to this key manager, we have implemented our own plugin in PDI. We have introduced a data structure that allows us to describe the spatiotemporal decomposition of our MPI data to facilitate the representation and thus the selections of the data. We have also introduced a new concept on Dask to support external data as input to the task graph, which is called external tasks, and implemented contracts to make selections easily in the generated data. In terms of architecture, the difference is that we don't have to send metadata at each time step. We have a new way to describe the task graph thanks to the external tasks in the scheduler. And to get all the information about this generated data, we have this contract step, which is done at the beginning of the simulation. We send those metadata only from bridge 0. And then the client will send back the selections of the data it wants, and that's all the connections that we have now of communicating the metadata. So the external tasks, we have implemented that, as I have said, in Dask. They can be seen actually in MPI as an enrolled loop where we have a task, an external point, a task, an external point, and so on. And from that point of view, those tasks are represented as inputs to the task graph, and they are included natively as any other task in the task graph. The advantage of that is that we can submit tasks to Dask even if we don't have already the data. And Dask will not schedule those tasks. It will wait until the data is available, and it will schedule a different task. The DEISA virtual array, if we have to describe it, is, as I have said, a spatiotemporal description. So if we have, again, the space as this dimension and the time in this way, we can represent it as an array of 2 dimensions. And of course, the dimension of processes can be n dimensions. And this way, we can represent or describe the simulation data globally over time steps, not only over space. So we give the global size and the subsize of each block given by each process and where it starts, which means that the mapping of this local data to the global data structure. So the contract operation that happened at the beginning of the simulation is the process 0 will get this description of the arrays from the configuration file. It will send it through the scheduler again to the adapter. This adapter will get it, create the external tasks corresponding to the arrays that it wants. It will give back the selection to the processes. There is a synchronization here, so the processes will not send the data before they receive the contract. When it is received, they will check if their selection is included in the arrays the adapter wants. If yes, we send it. If no, we'll not send, and this way we have a gain of communications that are not needed. And then we send the data. And this is done once, so we submit only one task graph at the beginning of the simulation. So there is no more communications between the adapter and the scheduler regarding the task graph. If we have to talk about the number of variables and queues that are used, so clearly we have less queues in the single graph version because we do not need them to communicate the data. Everything is done at the beginning, and the key management is not centralized as it was. So we do not need to send any more data. And for communications, we have, of course, less communications between either between the bridge and the scheduler or between the client and the scheduler. In terms of analytics, here we have clearly a better interface for non-incremental algorithm by default. For example, here we took the incremental time derivative that needs several time steps before it can start computing the derivative. We have we can just use the exact same algorithm here. And once the data is available, it will start computing rather than waiting for the next step before we can do that. And that's actually quite satisfying because the user does not need to manage the time dimension in a different way. So in this single graph version, we have time-independent task submission. We do not have to wait until the data is available to submit tasks. We natively support external tasks in the task graph. The user does not need to know how we manage that. We manage the time dependencies automatically, so we can have algorithms to start when the data is available. We can also make selections in the spatiotemporal data easily, which is also really needed in the community. However, we have static contracts, which is a way to select the needed data at the beginning. They are not updated, but it can be also interesting to update the contracts if needed data is needed. So for the results, we have performed several experiments in Rich and Irene supercomputer. We have used a mini app of 2D hit solver and two main analytics, the IPCA and the derivative. And in this presentation, I will just talk about the scalability, the variability, and the efficiency of this method. So here we have the weak scaling results, one of the weak scaling results of DEISA with its two versions compared to post hoc version. So here in X, first of all, this version is from the simulation. This figure represents the results from the simulation side. So we have the simulation in green, the communication, the post hoc right in red, and the communications here for DEISA. And the other side is for analytics, and I will talk about later. So clearly we see that Dask do not scale, weak scale perfectly because of the I/O bottleneck. So more we have processes, more we have a load on the parallel file system. However, it's better for DEISA versions because we do not have to go to the parallel file system. However, of course, we take advantage of the aggregated network, but we still have to go through the scheduler for small pieces of data. So here we see that the DEISA, the single, no, here actually it's a multi-graph, single graph rather than single method. So in the first version of DEISA, we have a lot of variability because of the load in the scheduler that is reduced clearly in the other version. And for this last configuration, for instance, the multi-graph version is 3 times faster in the simulation side than post-hoc with almost the same code in effort. And the single graph version is 7 times faster. In this figure, we have the analytics part. And here again, we have 2 versions of the PCA with 2 versions of the analytics. So the first one is multi-graph IPCA for post-hoc. The second is, so in orange, actually, the same order here. The second is single graph IPCA. The third is multi-graph IPCA in situ, and the third is a single graph IPCA, of course, in situ. So the first thing that we see is that for, or I have to mention first that the post-hoc version, it includes reading data for disk and the analytics. For DEISA, it is waiting for simulation data to be available and the analytics. So the first thing we see that is the multi-graph version of the APCA do not really scale perfectly. And when we only send a single graph, we have better performance for post-hoc because actually of the optimization of the task graph by Dask. Because when it has a global view of the analytics it does, it can make it better to work and optimize several communications and reading data from disk and so on. So for the DEISA versions, they scale better than the post-hoc versions, and that's ordinary. And the single graph version apparently is better than the multi-graph version. And even if we have the time we are waiting for data, we are even better than the post-hoc version. Here we have the strong scaling analytics for 8 GB problem, and the results are done as in terms of cost, our core costs. So for post-hoc, the cost increase when increasing the number of processes. The simulation is scaled perfectly. And for DEISA versions, we of course have better efficiency because we do not write data to disk. So we are faster and we do not consume a lot of resources. So for this last version, for instance, the first version of DEISA is 7 times faster, and the single graph is 16 times faster. And more we have processes, it should increase, this efficiency should increase. Actually, we have the same results from the analytics point of view too. So for the variability evaluation, we can see actually several versions. So that's actually only for DEISA. We see the communications of 1 gigabyte data for a problem with 28 processes. For the 3 versions, we have only the communication, which is shown. So in black is the communication, in red the variability over iteration. And so this first version is the multi-graph version, where we have a lot of metadata to send to the scheduler, so it causes a lot of variability. And we have also a lot of small messages sent by each bridge to the scheduler. In these 2 versions, it is both single graph version of DEISA. Here we have less metadata for both of them, The only difference is that we have reduced the number of heartbeats. The small messages are sent between the scheduler and the bridges. So clearly, between the two versions, we have less variability over iterations. However, we still have another variability, which is the position of the processes. And when we have checked that with the support of IRIN, we have seen that usually when we have an interesting time, the processes, workers, and scheduler are connected to the same switch. When it increases, they usually go through at least 2 switches to get to the different parts. So for the applications, we have used DEISA in 2 production use cases. So it has been integrated in Gisela, and we have run some preliminary experiments in IRIN. We have actually the results are not really interesting because the data generated by each process in Gisela are in the order of 5 gigabytes, and the serialization in Dask is not really interesting. So the results are not quite satisfying for the moment. So we can consider that for perspective. But also DEISA has been used in ARC2 MHD code in the scope of the Grand Challenge at Astra. And in that range, the machine has been integrally and has been used. We have used the integrity of that machine in those runs. And Ad Astra actually is the third in green fact analysis. So I will have to conclude and talk about the perspectives. So we have addressed in this work 2 main problems. The I/O bottleneck, so we cannot anymore write all the generated data to the simulation. And another issue, which is regarding that solution, which is the in situ. So we have reduced the in situ of we have reduced the complexity of the in situ to be able to get those 2 advantages from the 2 paradigms. For that, in computer science world, we have coupled MPI to distributed task-based programming. We have proposed this bridging model and implemented 2 versions and evaluated them using 2 algorithms and a mini app. And finally, we have shown interesting results, interesting performance results with the same coding effort, which is quite satisfying from the community point of view. And finally, DEISA has been used in 2 large-scale simulations that are Gisela and ARC-MHD. So as technical perspectives of this work, we can, first of all, address the technical limitations such as communications between the different bridges. We can think about avoiding going through the scheduler and make another way of communicating, such as in MPI. We can improve the placement of the scheduler worker bridges placement. We can think about improving the serialization algorithms for large data blocks. Another perspective is regarding supporting dynamic contracts and triggers that are interesting in the in situ world. When, for example, we detect an interesting event, it is interesting to get more data, for instance, to understand from where it comes and so on. And finally, it can be interesting to extend the bridging model for several configurations rather than considering only a producer and 1 consumer. It can be interesting, for example, for ensemble runs where we have several simulations producing the data rather than only 1. For general perspectives, we can think about exporting the idea of coupling MPI with task-based programming model outside of in situ analytics. For instance, we can only think about generating high-level code where we take advantage of task-based programming models for a piece of the code and take the advantage of high performance of MPI in another piece of the code. We can think about extending the bridging model to other programming models to take advantage of each of them, not only MPI and task-based programming model. We can think about exploring DEISA in the HPC-AI conversions in both directions. We have to mention that Dask has already supported to use PyTorch, so it's almost ready to use simulation data to be processed using AI models using only DEISA. And in the other way, also, if we consider a multi-producer, multi-consumer in the two directions. And finally, we can think about using those external tasks in Dask for other applications, namely digital twins, where we can have the data coming both from the simulation and real devices to understand a given problem. And that was it for me. Thank you for your attention.
Thank you.